if 1 is true, 2 is true, and also this critical, running this critical graph subroutine does in fact give me linkage. So why is that good? So here, right? If I here, if I did in fact have two vertices, two surface vertices u and v, so that I couldn't put anything between, I couldn't find the surface vertex with a changeover area between them. What would happen is I claim u with this k tuple as its changeover, and v with this tuple as its changeover. So u will be adjacent to v, right? Because everything, all the conditions are satisfied. Okay, so that's the point. I'll come back to this in a minute. Okay, so we constructed our auxiliary graph in this way, right? So again, I make this adjacent to that if when I look at this area, AP delete AQ, and I apply the critical graph subroutine, I get my linkage. Okay, and now the theorem is that there is a linkage in the B graph if and only if in the auxiliary graph there's directed path from y change y to x change x. So let's try and see why that is. So first of all, let's see that if there was a linkage, then this path would exist. Right? This path would exist in the auxiliary graph. Well, so let me go back to this picture. Right? So suppose there was a linkage, then I could in fact choose a bunch of surface vertices as close, so that consecutive pairs are as close together as possible. Right? There's nothing between them, and I have y and x. So I claim this would be a path in my auxiliary graph, right? Because let's just check that v4 is adjacent to v3, for example. Well, that's exactly right. So not v4 is adjacent to v3, but v4 with this guess at the changeover place is adjacent to v3 with this guess at the changeover place. So, but that's true, right? So v4 is adjacent to v3. That's from our theorem, and the out neighbors of v3 are a subset of the out neighbors of v4, and this bit is critical. So when I run the critical subroutine, I do get that this gray thing is adjacent to that orange thing. So it is true that if there was a linkage, then there are paths in the graph I started with. So what about the other way around? I need to check that if I found path in my original graph, then there was a linkage. So that's sort of similar. I don't want to do the details of that, but same thing, right? What does it mean that there are paths? Well, that means I can find, what does it mean there is a path in the auxiliary graph? Well, that means I can find a bunch of vertices with a bunch of changeover places and linkages between them. But what does it have to do with my original problem? Well, it's because I insist that the path goes from y to x. So I find a path in the auxiliary graph. I'm guaranteed that the first vertex of the path is y with those guys, and the last vertex of the path is x with those guys in the changeover place. So, right, so the algorithm in the auxiliary graph would tell me that, the existence of the path in the auxiliary graph would tell me that I can find, so I have my vertices T, so it's 1 to tk, and I have my vertices S, S1, S2, up to Sk, and what I'll get from the auxiliary graph is that I can find, a bunch of edges here and some paths between them, and then I can find a bunch of edges here and some paths between them, and some more. Right, so that's what my auxiliary graph gives me. So now I need to worry, can this intersect that? Or can this intersect that? And so you worry and it comes out that it's okay. But this is maybe enough details. And so thank you very much. We'll go 48 minutes.
We have some time for questions. So, is it possible to implement this program as this algorithm? Did you try? A student, not you, but
Nobody tried yet. I mean, I think it's possible, but
yeah,
but
very interesting exercise.
Yeah, I mean, it's hard. It's hard.
Yeah, very complicated. Yeah. So, what's the estimate for the running time?
It's about something like maybe the 30k cubed. So the k cubed comes from the fact when you build the auxiliary graph, right? So you need to go through all these possible changeover places. But in real life, the changeover place is not an edge, but a triple of vertices.
So it's a beautiful example of a polynomial algorithm. So it's not practical, unless.
Yes.
Yeah. But it's very beautiful.
Well, there's that n to the 96 algorithm to find this Q partition graph.
Right. That's very nice. And as far as tournaments, so you have somebody beat somebody else. So in this case, you have n people. You have like teams. Each one plays each other. So I guess the point is to find somebody beats somebody else, so they don't meet.
Right.
Yeah,
I suppose.
And the other problem is known to be NP-hard.
For general diagrams, yes. So maybe it's polynomial if instead of tournament you say the underlying graph has bounded stability number. That may be polynomial.
And when you do, so when k equals 2, it is faster than what's known before? The special case k equals 2?
I'm not sure. I don't know.
Yeah. But it's not the same. When k equals 2,
definitely not the same. It's definitely not the same.
So it's a new algorithm completely, even for k equals 2.
Right. I mean, I say it's definitely not the same. I mean, I don't know, maybe you can somehow very cleverly see that it's exactly the same, but certainly not said in the same way.
And you don't know what is best possible. It's possible with a better algorithm. I mean, faster. But it's the first one.
Yes, exactly.
Let's begin again. You're most welcome to join.